Hello everybody. In this video, I will analyze this closed-loop system using the root locus techniques. In the previous video, if you remember, I analyzed the stability of the system using the root locus method, and our goal was trying to find the range of k out and k in such that the closed-loop system is stable. The root locus can give also insight about stability, but it provides a much richer information because we now can technically track the dependence of the closed poles with respect to a parameter. Okay, so let's start with the assumption that, okay, because we have two parameters and root locus is based on plotting the root locus with respect to a single parameter, let's assume that k in, okay, so inner loop's gain is equal to 0. So in that respect, we don't have any like cascade loop, it's just single loop. We have a k gain and we have open loop transfer function which is equal to GOLS equal to simply 1 over s minus 1 s plus 1, and technically the system is in standard form. We can use the rules or the procedures of drawing root locus just looking at the closed on the open loop transfer function of the system. Okay, so let's look at the poles and zeros. As you can see, 0, we don't have any 0. We have two poles. Okay, so let's place the poles. One is here, one is here. This is 1, this is minus 1, and there is no 0. Okay, let's start with the real axis, which is the one of the easiest part of the root locus. Okay, so if you look at this region, as you can see, there is no pole in this part, so this is not located on the root locus. If we look this region, okay, so as you can see, there's one pole or 0 totally in this part. So this part is technically inside the root locus. So let's change the color. Okay, if I can do that, I can do that. Good. So this part is in the root locus. Okay, so if you remember, the root locus starts from the poles and goes either zeros or infinity. So technically we have this direction for the poles. Okay, so at some point they will meet each other, which creates a breakaway point, and they will go to zeros, not zeros, because we don't have any 0. They will go to infinity. Okay, so how many asymptotes? Of course, it is 2 minus 0, so we have 2 asymptotes, and they will go to infinity. Okay, so how we compute the angle of the asymptotes? Actually, this is very easy. It is 90 degrees, but if you remember, the formula is this, okay? Phi a is equal to plus minus pi 2k plus 1 n minus m. Okay, so we have only like 2 poles, so k will be equal to 1 and 2, and if you do that, you will see that it is 90 degrees and minus 90 degrees. Okay, that's great. So we know that we have a like one of those asymptotes will go to here and the other asymptote will go to here. Okay, so what we can do is we can compute the breakaway point and we can compute the intercept of asymptotes. Let's start with intercept asymptotes, which is quite easy for this case. Okay, sigma a is equal to summation of poles, which is equal to 0. Okay, summation of zeros, which is of course equal to 0, and minus 1 is equal to 2, so it's equal to 0. So the intercept of asymptotes is actually happening at s equal to 0. Okay, that's nice. So we know that the asymptote is going in this direction, the other asymptote is going in this direction. So where is the breakaway point? Okay, root locus is technically, you can think of like it tries to find the easiest path. So if it will go here, and due to the symmetry, it won't do something like this because it cannot do that, right? Okay, because at some point they should meet and leave. Okay, so and it can be any part. But if we do it here, it doesn't seem right. Okay, so indeed for this system, root locus is simply this. Okay, this point is the intercept. Let's change the color. Okay, this is the like intercept. It's also the breakaway point. Okay, and this is the root locus of the system. Okay, let's compute the breakaway point also. Okay, as you can see, which is quite easy from the system. So how we can compute the breakaway point? Okay, so there are different ways of computing the breakaway point. There are different formulas which are equal to each other. I will use one of them in this lecture. Okay, so G all of S. Okay, G. Okay, so for that. So let's change the color again. G O all of S is equal to 1 over, let's open the numerator. I think it's equal to S squared minus 1. Okay, so if we compute 1 over G all of S, 1 over G O L of S, okay, which is equal to S squared minus 1. Okay, so what are we going to do is we take the derivative of this with respect to S, okay, and equate to 0 to compute the breakaway point. So if we compute the derivative with respect to S, we will find that it's equal to 2S, okay, and if we equate it to 0, we compute the breakaway point, which is simply equal to 0 for this problem. Okay, so as you can see, the root locus is very straightforward. We have two poles that are meeting at s equal to 0. We have two asymptotes. One of them is going to like 90-degree infinity, so on the imaginary axis. Other one is going minus 90 degrees, which is going to negative part of the imaginary axis, going to infinity. And this is the basic idea. Okay, so what we can talk about the behavior of the system. Okay, so of course, this pole is unstable, this pole is stable. Okay, so until they meet it at some point, which is here, as you can see, it is always stable. Okay, they meet each other and they stay on the major axis, so it is marginally stable, and we know that it's bistable. This says that if Kn is equal to 0, the system can never be stable with just K out, so we cannot stabilize the system. We don't need to talk about the overshoot, transient response, and other things, but this system is indeed bistable. Okay, so what I want to do is, I want to also compute the gain at this point. I know that this is at the root locus because I already plotted root locus. So how I can compute the K, which is very easy. So technically the K should, this pole should satisfy the closure transfer function or the magnitude condition. So what I do is, I compute this. So K is equal to, since we are interested on the positive gains, 1 over, okay, GOL 0, because 0 is the breakaway point. I'm interested in computing K here. Okay, so in that respect, K is equal to, okay, 1 over magnitude of minus 1 multiplied with 1. That's great, so it is equal to 1. So when K is equal to 1, the system becomes a double integrator, okay, or something like that. You know that it is still Bibo unstable.